Everybody. We're getting ready to do lesson 11.4 part 1 classwork today for pre-calculus math. And 11.4 part 1 looks limits at infinity and limits of sequences. 14 points here in your notebook and 32 points here into your classwork sheet. Classroom students, name, date, period, and then onliners, homeschoolers, put your due date here. And we're going to go into our bell work for today, teachers and students. Sketch the graphs of y in each transformation on the same rectangular coordinate system for here. So each one of these put over here. And then down here, find the sum. So find the sum here. Check back in about 5-6 minutes, teachers. See you in 6. Hello, everybody. Welcome back for today's solutions. Today's bell work for 73 up here. Y equals x to the 4th power. Then we have each one of these transformations here. And this is what your graph should look. You got A over here. You got B here. This one down here. And then C drops down a little bit lower than B, so -2 plus x fourth, and this is -1 in x to the 4th power. And then D is over here. D is f of x equals 1/2 quantity x minus 4 to the 4th power, and you have a shift here to the right of 4 units for D. And then down here for 75, the sum is 5 plus 7 plus 9, 11, 13, 15 equals 60 here for that 6. So we have 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6 plus 3, and that all equals 60 there. Okay, so moving into our notebook, first notebook slide here. Limits at infinity and horizontal asymptotes. As pointed out at the beginning of this chapter, there are 2 basic problems in calculus, finding tangent lines and finding area of a region. In section 11.3, you saw how limits can be used to solve the tangent line problem. In this section and the next, you will see how a different type of limit, a limit at infinity, can be used to solve the area problem. To get an idea of what is meant by a limit at infinity, consider the function f of x equals x plus 1 over 2x. The graph of f is shown here. Here's your graph here. It splits out like that. From earlier work, you know that y equals 1/2 is a horizontal asymptote of the graph of this function. Using limit notation, this can be written as follows. As x goes to -infinity, f of x equals 1/2. So here's our horizontal asymptote to the left. We have -infinity, so it's coming in as it goes to the left in an infinite way. F of x will equal 1/2. Horizontal asymptote to the left. And then the limit as x goes to infinity will be f of x equals 1/2. Will be a horizontal asymptote to the right. These limits mean that the value of f of x gets arbitrarily close to 1/2 as x decreases or increases without bound. So that's what this basically means here. These 2 limits here mean that. Definition of limits at infinity. If f is a function and L1 and L2 are real numbers, then the statements, the limit as x goes to -infinity, f of x equals L1, and limit as x approaches -infinity. And the limit of x goes to infinity, f of x equals L2, limit as x approaches infinity, denote the limits at infinity. The first statement is read, the limit of f of x as x approaches negative x is L1. And the second is read, the limit of f of x as x approaches infinity is L2. Wow. To help evaluate limits at infinity, you can use the following definition. Limits at infinity. If r is a positive real number, then the limit of x goes to infinity, 1 over x to the r power equals 0. There will be a limit toward the right. Furthermore, if x to the r power is defined when x is less than 0, then the limit as x goes to negative infinity for 1 over x to the r power would be a limit towards the left. So what does all this mean? Let's try an example here. Evaluating a limit at infinity, find the limit. The limit of x goes to infinity for 4 minus 3 over x squared. So for this specific case, use the properties of limits listed in section 11.1. You should have that in your notes, students. And that's what we're going to refer to here. The limit as x goes to infinity for 4 minus 3 over x squared equals the limit as x goes to infinity for 4 minus the limit as x goes to infinity for 3 over x squared. And this can be further reduced down. We pull this 3 out here, and we have this factor out in front here of this limit, 1 over x squared. And then we can reduce it to this. 4 minus 3 times 0 will equal 4. So the limit of f of x equals 4 minus 3 over x squared as x approaches infinity is 4. Because as this goes to infinity, this number gets smaller to the point where it's pretty much 0. Use a graphing utility to graph y equals 4 minus 3 over x squared, and this is really what your graph will look like here. It will look like this, and if this is your asymptote here at y equals y will equal 4 up here. As x gets larger here, y will become closer and closer to 4. And same thing over here on the negative side. It'll do the same thing on that side as well. So the line y equals 4 is a horizontal asymptote to the right. You can use the trace feature to determine that as x increases, y gets closer to 4. And that's what you have here. So let's try one. Find a limit if it exists. If the limit does not exist, explain why. Use the graphing calculator to verify your result graphically. So the limit as x goes to infinity here for 3 over x squared. And then students, this is yours down here. But up here, what we have is as x goes to infinity here, 3 over x squared will be virtually 0. It'll be virtually a 0. And then down here, students, I want you to work that one. Oh, I look at that, I threw that in. Same thing here. As x goes to infinity, your denominator gets larger and larger, and it makes your number smaller and smaller. The line y equals 4, which is here, is also a horizontal asymptote to the left, so it goes this way as well. You can verify this by showing that the limit of x goes to negative infinity here, negative infinity, times to the 4 minus 3 over x squared equals 4. Same thing as it goes this way. Your f of x will equal 4. The graph of a rational function need not have a horizontal asymptote. When it does, however, its left and right asymptotes must be the same. When evaluating limits at infinity for more complicated rational functions, divide the numerator and denominator by the highest powered term in the denominator. This enables you to evaluate each limit using the limits at infinity at the top of this page. So there is a rule there that you can use for when you take limits at infinity. Comparing limits at infinity, find the limit as x approaches infinity for each function. So we have a here, f of x equals negative 2x plus 3 over 3x squared plus 1. So in each case, begin by dividing both the numerator and denominator by x squared. So when we do that, the highest power term in the denominator is right here, x squared. When we do that, we end up with this complex fraction up here in the numerator, divide it through by x squared. We end up with this up here, basically, as x goes to infinity here. These numbers get smaller and smaller. This number here does not have an x in the denominator, so it just becomes 3. So we end up with basically 0. We have 0 over 3, which is 0. Okay, so for b here, negative 2x squared plus 3 over 3x squared plus 1, when we have that and we take as x goes to infinity, again we end up with a complex fraction here. We're going to divide through by x squared on each one of these. This goes away, then we have 1 over x squared, then we have 3 over x squared here, and then this becomes negative 2 over 3. So as it looks, this becomes negative 2/3 when we take this limit to as x goes to infinity. And then for c equals negative 2x cubed plus 3 over 3x squared plus 1. And when we have that, when we divide through everything by x squared, this becomes negative 2x. This is 3 over x squared. Then we have 3 plus 1 over x squared as x goes to infinity. In this case, you could conclude that the limit does not exist because the numerator decreases without bound. This decreases here without bound because of this here, and this is negative as well. So it decreases without bound as the denominator approaches 3 here. This approaches 3 here. So we're going to go into this now. If the limit does not exist, explain why. Use a graphing calculator to verify your result graphically. So we're going to, again, we got negative infinity, x goes to negative infinity, and this is the same thing, x goes to negative infinity down here. So for 19 up here, what we have here, as x goes to negative infinity, we're going to divide through again by x squared, and when we do that, we'll end up with 4 up here in the numerator, and then negative 3 over x squared, that'll go to basically nothing, 0. And then here we can divide this by x squared. We end up with a negative 1. So we end up with negative 4 here for our solution to 19. In example 2, observe that when the degree of the numerator is less than the degree of the denominator, as in part A, the limit is 0. When the degree of the numerator and denominator are equal, as in part B, the limit is the ratio of the coefficients of the highest powered terms. When the degree of the numerator is greater than the degree of the denominator, as in part C, the limit does not exist. So we have 3 different conditions here to consider. This result seems reasonable when you realize that for large values of x, the highest powered term of a polynomial is the most influential term. That is, a polynomial tends to behave as its highest powered term behaves as x approaches positive or negative infinity. So that's a good note there to take down and to remember. And that is 11.3 part 1, pre-calculus math. Oh, I'm sorry, it's 11.4 part 1. 11.4 part 1, pre-calculus math. Animated PowerPoint math video at AOL.com for course materials and/or questions. Thank you very much.